Yeah, good morning. I am Dr. B. Jyouthi, working as Associate Professor in St. Peter's Engineering College in the Department of AI&ML. Today, let us have a discussion on Booth's algorithm. This is mainly used for the multiplication of the two digital numbers, which are represented in a 2's complement representation. So here, hardware implementation of Booth algorithm is shown here. Before going to this one, let us have a small example. Let us take the decimal numbers, which are 5 into 4, which are performing the multiplication between the two numbers, which is 20, as we know that. If we represent the same thing in a binary notation, the 5 is represented with the 0, 101, and 4 is represented with the 100. So here in this multiplication process, 5 is called the multiplicand, 4 is called the multiplier. So here the multiplication operation is done bit by bit. The first 0 is multiplied with the 4 digits, 4. And next also we have a 0. 0 is multiplied with all bits, again 0. 1 is multiplied with all, which is nothing but 1 0 1 0. And the last one is also we have a 0. If we add all these things, it is 0 0 1 0 1 0 0. So this is in a binary notation. Let us convert this into the decimal notation, where the conversion process is multiplied with the base 2 power corresponding powers, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, where 1 into 2 power 4 plus 1 into 2 square, which is nothing but 16 plus 4, we got 20. So this is equated. 5 into 4 is 20, we got 20 in a binary notation also. To perform this multiplication, the hardware implementation is shown here, where it contains the BR register, QR register, and accumulator register. In a BR register, we are storing the multiplicand value. In a QR register, we are storing the multiplier value. So after multiplication, the resultant is stored in a accumulator. In between this process, while we are performing the multiplication between these two, we have to go through some of the complementation operations and the addition operations. For that, this block will take care of those complementation operation and addition operation. Apart from this, we are also have a sequence counter. Here, the sequence counter is counting the number of operations. So this sequence counter stores the number of bits which are stored in a multiplier. So our multiplier is 4, which contains 4 bits. So here, sequence counter contains 4. And one more here, we have a Qn and Qn plus 1. These Qn plus 1 bits allows us to perform 2-bit inspection. So regarding this, we'll discuss in detail in the flowchart, where Qn is nothing but the least significant bit of the QR data. Register Q contains 4. 4 if you represent a binary format, 100. So this is nothing but a least significant bit, and this is nothing but most significant bit. So this least significant bit is represented with the help of represented by Qn. Next we have a Qn plus 1, which is a flip-flop which stores a single bit of information. This Qn and Qn plus 1 combinedly helps us to perform the 2-bit inspection. That we'll see in a flowchart. So this is what about the hardware implementation and the simple multiplication process. Let us have the same multiplication with the help of the flowchart. So this is a corresponding flowchart of the Booth's algorithm. Before starting that, we have to initialize the BR register B and the register Q. Multiplicand is stored in B register and multiplier is stored in a Q register. Once it is stored, we have to initialize other registers also. We have an accumulator as well as a sequence counter and the Qn plus 1. So first accumulator is initialized with 0, and Qn plus 1 flip-flop is also initialized with 0, and the sequence counter is stored with n, where n is a number of bits. In our case, it is 4. So after that, we have to go for the 2-bit inspection. What are those 2 bits? Qn and Qn plus 1 combinedly called the 2 bits is used for the inspection purpose. If the combination of Qn, Qn plus 1 is 0 0 and 1 1, we have to perform the right shift operation. Once the right shift operation is done, we have to decrement the sequence counter. After decrementing the sequence counter, we have to check that whether the sequence counter reaches to 0 or not. If it is reaches to 0, we have to end of the process. If it is not reaches to 0, We have to go back again for the comparison purpose. Inspection of again 2-bit Qn plus 1 bit has to be inspected. For example, if the Qn plus 1 is having 1-0 combination, then we have to go for subtraction operation here. When the combination of the Qn plus 1 is 0-1, we have to go for the addition operation. Here, when 1-0 combination, we are going for the accumulator plus register B, complement of register B plus 1 is to be done. So this is also represented with AC minus BR. So this operation is a 2's complement subtraction. Let us have the flowchart, understanding of the flowchart with the help of the example in an easy method. So for that, we have to take the initialize the sequence counter, first case. So we are taking all the bits, initializing. We are arranging all the bits for easy purpose. Later on, we have to take the accumulator. A accumulator contains 4 bits. This is also represented with the help of the 4 bits. Next, I am taking the Q register. What is there in Q register? Qn register QR, which contains the multiplier. In our case, it is 100. Next, Qn plus 1. Next, what operation we are performing? Let us have a simple notation here. First, our sequence counter is 4. Accumulator, all the values are zeros. And the register Q contains 4 value, which is 0, 1, 00. Here this place is Qn place. This is Qn place. Qn plus 1 is initialized with 0. We are initialized. First step is done. Later on, inspection has to be done between the Qn and Qn plus 1. What is this combination? 0, 0. We got 0, 0. When it is 0, 0, what has to be done? Arithmetic right shift has to be done. Arithmetic shift right or arithmetic right shift. Arithmetic right shift on what? Entire sequence we have to. What is the entire sequence we have here? Accumulator, QR register, Qn plus 1. On this entire sequence, we have to perform AC, comma Qn, Qn plus 1. Q and QR plus 1. We have to perform the right shift operation. Means all the bits have to be shifted right by 1 bit position. 1 bit means a single bit has to be moved out. If it is moved out, the Q0 will come into this position. Right? Qn will become Qn plus 1, occupies the Qn plus 1 place. This Q0 will be occupied by the Q1. Q1 is occupied by the Q2. Q3 will be, Q0 is went out here. Q0 will be occupied by Q1. Q1 will be occupied by Q2. Q2 will be occupied by Q3. What is there here? 0. What about the Q3 position? We are shifting all the bits. No? We are shifting from A, QR and Qn plus 1. So if Qn plus 1 is going out, the Q3 will become Q2 and the Q3 we occupied with the A0. This bit will come here. And similarly, all the bits will be occupied like this. Second is second and third is third. And what about the last bit? A3 is vacant here. In arithmetic right shift, whenever it is happening, right shift is happening, the most significant bit will be replaced as it is and it is moved to the next also. Based on that concept, we will have a 0 here. So we have performed this operation now. So we have inspected the Q and Qn plus 1 because we got the combination 0, 0. We are performing arithmetic right shift. Once it is done, what is the next operation we have to do here? Decrement the sequence counter. What is the value of sequence counter now? What has to be? Next has to be 3. Then this is one set of operation is done. Again we have to check the sequence counter. What is the sequence counter value? 3. Is this 3 is that? Not, it is not 0. So we have to go back. Go back to the again 2-bit inspection. What is the 2-bit inspection? Qn plus 1. Again we'll check this Qn plus. What is again the combination? We got 0, 0 we have again. Again 0, 0 means again we have to go for the arithmetic right shift. Arithmetic shift right of A, QR and Qn plus 1. Let us apply on that. In that case, this 0 is going out. This Q0 will come, Qn plus 1 place. This is occupied with the next bit. This is occupied with the next bit. And next bit, and this is occupied with this bit. This is occupied with the next bit. Like this, the operation. Right shift is done here. When it is right shift operation is over, the sequence counter will be decremented by 1. Yes, done. After that, again check the sequence counter here. It is not 0. Go back. Again, go 2-bit inspection. And now let us go to the 2-bit inspection. What is this combination? 1 0. 1 0 happens. What we have to do? This operation we have to do. Once we have done 2-bit inspection, the combination is 1 0. So that's why we are performing this operation. Here, let us have, what is the BR value? What is B register contains? Multiplicand. What is our multiplicand? 5, which is nothing but 0 1 0 1. What is corresponding BR? Complement of BR means now 1 0 1 0. Complement means 1 will become 0, 0 will become 1. For this, apply the 2's complement, which is nothing but 1 to be added to the 1's complement. 1 is added here. The final answer is 1 0 1 1. We have done BR plus 1. This is to be added to the accumulator. This BR plus 1 is added to the accumulator data. What is accumulator data? 4 zeros. This once it is added now. 1 0 1 1 is added here. So we are performing plus operation. What is the answer? 0 plus 1 1, 0 plus 1 1, 0 plus 0 0, 1 plus 1 1. So here, after addition, we have to again come back to the arithmetic shared right shift. Arithmetic right shift on again A, Q, R, Qn plus 1. Is it not? So that's why instead of having clumsiness, I am rewriting the QR also in the next stage. 0 0 1, here again 0. I am writing so that I can have a shift easily. Now apply the right shift on this sequence. Arithmetic shift right. So this bit will go out. This 1 will come here. And this 0 0 0. And similarly this 1 will come here, travels here. Next this 1 here is 0 1 0 0. This 1 will high. This 1 will be here because it is replaced MSB as well as it will be shifted. Done. Next, once it is right shift has been done, this has to be decremented by 1. Yes, no? Yes, once it done. Again we have to check the sequence counter. Is this 0? No. We have to go back to the 2-bit inspection. 2-bit inspection, the combination is 1 0 0 1. So we have to go with the AC plus BR. What is BR value? BR value is nothing but multiplicand 0 1 0 1. So we have to multiply it with the 0 1 0 1. After multiplication, this is 0, carry 1 plus 1 0, carry 1 1. 1 plus 1 0, carry 1. 1 plus 1 0, carry 1. Here the carry will be generated. So in 2's complement, neglect the carry. As for the 2's complement, arithmetic operations, neglect the carry. After performing the addition, we have to go for the shifting operation. So for shifting operation, I am again rewriting this QR so that for easy purpose 0 and 1. Now apply the shift operation on this. If it is shift operation, it will go out. This will 0 0 0. This will come here. Next 0. Next 0 is shifted here. 1 is next remaining shifted. So once arithmetic shift is done, the sequence counter will be decremented to 0. So once the sequence counter is 0, we have to end of the process. So let us check the result, whether it is right or not. So here again this convert back into the decimal format. This is 2 power 0, this is 2 power 1, 2 power 2, 2 power 3, 2 power 4. So 2 power 4, our result next is 1 into 2 power 4 plus 1 into 2 power 2. This is 16, This is 4. Finally, we got 20. We got 20. In this fashion, we are using the Booth algorithm for multiplication of the two numbers. Thank you.